Let's keep moving forward with this concept beyond the Hadley cell. We did the Hadley cell. It does the job it's supposed to do. There are additional complications. We'll see that how much energy is the Hadley cell actually moving from low latitudes into the subtropical high extent at which it terminates, right? Without saying how it terminates, we'll move into the mid-latitude weather systems. The figure we have seen before, an instantaneous 12 GMT geopotential height and surface pressure field and surface wind field on June 21. So on the surface, you can see that this is at 80 west. This line here is going along 80 west. You have to remember you're on a sphere with increasing latitude, so that's a pretty large latitudinal range being shown here. The point really is that as you go from lower latitudes to higher latitudes, you will begin to see more and more unsteady flow. Hydrodynamic instability basically means the system will be full of eddies. So that's what these are, various scales of eddies. Okay, this underneath, I don't know if you can see it clearly, but there is a US map, and so you have gone past the Hadley cell here by the time you reach a latitude of about 45 north, and you are going from the Pacific into the Atlantic Ocean here. And you can see that the you can imagine maybe there is a summer kind of pattern with jet stream basically being northward still. Why? Remember we said jet stream is strongest in the winter hemisphere. This is in June, so obviously it's northern hemisphere summer. So the air masses that come here would be of a different origin in the summer than in the winter months. Okay, we will see that a little bit more later on. The main point to remember here is that there is nothing like this nice meridional mean, zonal mean meridional section we've been showing, saying there are westerlies. You don't see hardly any westerlies at these latitudes north of the Hadley cell. Okay, so this is again now the 500 millibar height with the height surfaces on constant pressure height contours on a constant pressure surface, 500 millibar surface, and here we said the height drops from about 5.8 kilometers down to about 4.9 kilometers, and again the main thing is here is that looking at any particular day of particular time, you will basically just see a bunch of eddies. So you are going from the tropics here, the northern edge of the South America and Africa here, into the latitudes where we said hydrodynamic instability occurs. This we showed this before, and we talked about it in the context of Rossby numbers and so on, but we didn't say what caused these features, these eddies of lows and highs. So here is again the same thing taken as a section through at 80 west. So you can see that blown up again on the US. It's the same figure we saw before. You clearly see the eddies, and in a temperature field as well we had seen the eddies. This is just reinforcing that in fact angular momentum breakdown does happen, hydrodynamic instability does happen, there are eddies floating around at mid latitudes and beyond. This is what gives it the stormy character of the weather. Okay, there are additional details about tropical weather versus mid-latitude weather which we will not get into. So what's happening here? Now you imagine our nice potential temperature profiles that we saw. zonal mean meridional section showed that potential temperatures tilt upwards towards high latitudes from the low latitudes, and if you took a section through the atmosphere at any particular location, we remember that the temperature would decrease with height, whereas potential temperature increases. So if you're moving, as I said before, air parcel from near the surface at low latitudes to higher latitudes, warm air from near the surface to high latitudes, it would be going up the potential temperature surface or across it, right? So that's kind of what we are trying to do here. We're going into the mid latitudes, and we are saying here is our nice large scale wobbly pattern that we had kind of hinted at before. So cold polar air or mid latitude is pushing down into the subtropics, and warm subtropical air is pushing into the higher latitudes, mid latitudes. Okay, so now you cut through it and you look at the movements in temperature profile. So here you have cold mid-latitude temperature and warm subtropical temperature. I might have to stop it because there is a chopper buzzing by, so let me pause it. Continuing, we are pushing cold polar air towards warmer subtropics and warm subpolar air towards the mid-latitudes. You look at the isothermal profiles. You have sharp fronts as the cold air pushes into warmer air. Let's see, pushing down. So you have cold air pushing down into the warm air, and warm air rising over colder air. Okay, so you have these eddies. So this eddy is taking warm air north, this eddy is bringing cold air south, and warm air north, cold air south, right? So you have this large scale wobble that we are talking about here, within which we have embedded eddies. So cold air is pushing into a warm air. That typically happens on a smaller scale called cold front, and warm air pushing into the cold air mass that's sitting there. It's called a warm front. And why are these sharper like triangles here, and why these are smoother like semicircles here? It turns out that heat transport by these mid-latitude eddies happening this way does in fact create sharp fronts when cold air pushes into the warm air, because cold air is heavier and denser, so it's pushing into the warm air, and the warm air is just forced to rise and convect ahead of the cold front. Okay, so the scale of this cold front typically is 75 to 150 kilometers, whereas when the warm air pushes into a cold air mass that's sitting there, warm air is forced to rise on top, because think of me pushing some big guy. I'm not a very big guy. Then obviously I cannot push the big guy. Okay. Do I have to climb over him? I don't know, whatever the analogy. So warm air rises on top of the heavier cold air. As it rises, it expands and cools and condenses and pumps more energy into it and keeps going. So the scale of the warm front is much larger typically than a cold front. Okay, that's essentially what's happening here. Cold air pushing down into the warm air creates sharp fronts, whereas warm air rising over the cold air produces a longer spatial scale and smoother fronts. Okay, they are not even fronts, even though they are called warm fronts and cold fronts. So intuitively think about how the mid-latitude exchange is happening with these eddies. But the eddies we showed here were just circles. We'll see soon that circular eddies will not do the work of transporting heat across latitude lines. We always have to look for energy moving across latitude lines, because the energy has to move steadily from lower latitudes to high latitudes to do the energy balance. That's where we are headed. What exactly are the processes by which this is happening? Okay,